Hey, Math 137. In this video, we're going to be looking at a little bit of trig trivia. These are some ideas that aren't necessarily going to help you do Math 137 homework problems. They may not even help you understand the trig functions any better in a way that's beneficial for our class. But the ideas that we talk about in this video, they might help answer some questions that you have, questions that you maybe thought were important, but turn out maybe not to be so important. So I think it's a good video to watch. It's definitely interesting information. Again, just because it's not helpful for us in our class doesn't mean that it's not interesting information. So, and it might actually help you. So we're going to be looking at a couple different pictures here. In the first picture, we're going to be looking at some in this first case about some of the history of trigonometry, so that we can maybe understand the words that we're using a little bit better here in this class. So back in the day, they used to think that the diameter of a circle was very important. Today, we focus more on the radius of a circle, but back in the day, they thought that the diameter was important. So we're going to be looking here at a circle whose diameter is 1. We've been focusing on the unit circle with radius 1 in class, but let's talk about the circle with diameter 1 first. All right, so now that we've established that this circle has diameter 1, let's go ahead and get this out of here because we don't need it. It's going to clutter up our picture. Again, we're just talking about a circle whose diameter is 1. And we're gonna drop a couple of lines in here. And these are called chords of a circle, lines that cut across the circle. And we want these two chords to kind of share a point on the circle. And then we're going to draw one more chord here. Where'd my chord go? I had another chord. I don't know where it went. I'll just do it freehand, or I guess I'll get my ruler out. We want to where these two chords intersect the circle. I guess, and the word that I'm using here is CHORD, kind of like the music chord. Again, a chord is just a line that cuts across a circle. Now, if I take these two chords and draw the line that connects them, 89 degrees is probably the best because I didn't draw perfect, or maybe 88. We want this to be roughly correct. So if I draw another chord across the circle, picture that looks like this. All right, now those first two chords defined an arc length. So back then, rather than focusing on angles, we can have an arc length here. And let's call that arc length S. And then this last chord that we just drew has, maybe I wanted to call this T. Let's call this T. This will be better. Call this T, and let's call this one S. Now that red shape that I just drew looks like what a child might draw if you asked them to draw a bow. Remember like a bow and arrow, like Katniss Everdeen. All right. And S is the bowstring. The bowstring of bow T. Right, so T is the bow, and S is the bowstring. All right. Now, if we have this angle theta, now these two first chords described an angle theta, and it turns out that if we measure, again, this is a circle with diameter 1. If we measure the angle theta in radians, the angle theta measured in radians is the same as the length of the bow T. All right? And it turns out, and this was a fun exercise for me, it turns out that the length of the bowstring S is sine of theta. as an angle. So if we were talking about rotations, or even, I guess it looks like, I think theta here is an acute angle. So if you were talking about right triangle trigonometry, the length of the bowstring S is sine of theta. As an angle, it's also sine of t. When we learned about trig functions of real numbers, it's also sine of t. Right? So remember our trig functions, if we interpret our arc lengths as angles measured in radians, our trig functions are the same. Okay? So here's a little bit of etymology, history of the language. Right? Back in the day, in Sanskrit, Sanskrit was the language that they spoke in India. Okay? And there's a Sanskrit word, J-Y-A, with a line of, I don't even begin to know how to pronounce that word. I'm looking on Wikipedia as we speak, all right, for the etymology of this word. All right? This was the word in Sanskrit. That was an ancient language. Actually, I think it might be the first language. I have to go back and look at my history of languages. I think Sanskrit was one of the very first languages that humans ever invented, written languages. All right, in Sanskrit, the word, I'm just going to call it ja, means bowstring. And the Indian folks that were doing trigonometry, that's the word that they used. They said the ja of t. Okay, so the length S would be the bowstring, literally bowstring of t. And there were some other synonyms. You know, just like in English, we have synonym words different words that mean the same thing. And apparently, the word jiva also means bowstring in Sanskrit. Jiva T. So S is, now I guess we're using the equal sign as a shorthand for is. S is, I don't know the Sanskrit word for is. S is Jiva T. All right, so at one point in time, we had some mathematicians, Arabic mathematicians. There was the Arabic world was a big in the development of mathematics. Some Arabic mathematicians ran across these Indians, and Jiva T in Sanskrit was translated into Arabic as Jiba T. All right, it was just a transliteration. They replaced the letter V with the letter B. And I don't know if the word jiba meant the same thing, meant bowstring in Arabic, but that was just the translation that the Arabics did. So S is jiba T. And now maybe it no longer means bowstring. At some point in time, that got shortened. S is GBT. Right? They got lazy like most mathematicians and started cutting out letters. S is GBT. And then someone later came along and said, wait a minute, what does JB mean? I guess it means, now there's another Arabic word, JAYB. S is Jabe T. Where the Arabic word Jabe translates into something roughly like fold or bosom. All right, so along this process of translation and transliteration, maybe the Arabics didn't have a word or letter for V, so they just replaced it with a B here. All of a sudden now, S being the bowstring, which makes sense, S being the bowstring of T got translated into S is the fold of T. Now, there is some argument as to whether this bad translation was a result of Arabic translators or possibly European translators. So I guess we maybe can't blame it on the Arabic folks of ancient times. But then this Jabe T got translated into Latin sinus. Okay, so S is sinus t. Right there, the Latin word sinus also means fold or bosom in Latin. And a lot of mathematics in Europe back in the day were done using Latin. And now it's just a quick bit of saying, oh, S equals sine t. Replace the is with an equal sign, shorten sinus to sine. That's why the name is what it is. So if you're looking for an explanation for why we say sine of t, there it is. Again, I don't think that's going to help you get any problems done in Math 137, but it might maybe alleviate some of your worries about why do we call this thing sine of t, right? I guess if all of the translations had been correct, we would be saying, hey, S is the bowstring of the bow T. But unfortunately, our translators were not all great back in the day. They're not all great today either. All right, so there's a little history of the etymology of at least a piece of the language. We're going to learn a couple other pieces here in another example, as well as see some relationships, some geometric relationships between our 6 trig functions. All right, so here we're back to a unit circle. This is a circle here that has radius 1. So I'll draw in a quick radius here if I can manage. That's a reasonably straight line. So this circle again has radius 1. We're back to the unit circle. All right, now we're going to draw a line that cuts across the circle right through the center. All right, and this is an example of what's called a secant line. All right, secant roughly translates into cut. And whatever I don't even know the language. All right, those of you who end up taking some calculus, you'll see another version of a secant line as it relates to graphs of functions. Right, but secant roughly corresponds to cut in Latin or Greek or I don't know. And then another line, I'm going to take another line here. I'm going to have this one be at an angle. Let's flip this guy around so it's kind of at an angle. I'm going to place this line so that it just touches our circle at exactly one spot. Okay, so this is an example of what is called a tangent line. A tangent line that roughly corresponds to touch. Our tangent line just touches the circle. Okay, rather than our secant line, which cuts across it. I guess if we moved our tangent line just a little bit, there's another secant line. That's a secant. That secant line doesn't pass through the center like our secant line does here, but that's another example of a secant line. If we move this guy just so instead of touching at 2 spots, it touches just at 1 spot. This line doesn't cut through the circle, it just touches the circle. All right? So we have our secant line that cuts through, our tangent line that touches. I'm going to get rid of our radius here because it's just cluttering up the picture. Then I'm going to draw one more line in here that is another secant line that is perpendicular to the original secant line. Okay, so we've got basically 2 secant lines. One is our main secant line, the one that we're calling the secant line, and the other being the tangent line. Now I need one more line here. Oh God, this one might be tricky. My controls are off. I want to draw one more line here that goes from the point of intersection of these 2 secant lines through the place where our tangent line touches the circle. That looks to be about right there. Okay, so there's one more line. All right, now we're done drawing lines here. So here's our picture. Here's our picture. We've got a secant line that cuts, a tangent line that touches, and then a third line that's perpendicular to our secant line, and then another line another secant line. We got a bunch of secant lines going through the center here. Now our original secant line and this very last line, I guess, sorry, yeah, the original secant line and this very last line, they create an arc length as well as an angle. I'm going to call this arc length T. Crap, I need one more line. Actually, I need two more lines. I'm going to copy this guy. We got a lot of lines here. That's why I'm kind of trying to be careful with this picture. I'm going to copy this line. This line is going to come down. We'll get this line placed a little bit better. And then another line parallel to this one up here. So it also copied our perpendicular. Okay. Again, lots of lines here. That's why I'm being kind of careful here with the picture, because it could get messy real quick. All right, so we got an arc length T identified as well as an angle theta. Now remember, our circle had radius 1. So this length right here, now we're going to start to get really messy. This length right here is 1. This length right here is sine of theta. Or sine of t if we're worried about arc lengths. Let's worry more about this angle theta here. I like to worry more about that angle theta, so let's forget about arc lengths. We already did an example where we focused on arc lengths. Let's focus on angles. Let's forget about this arc length t for a second. All right, and I accidentally erased some of my garbage down here too. It's fine. It's fine. All right, so we got one. Maybe I think I want these to be the same color. Got a blue angle. Got sine of theta. This length right here on our tangent line is tangent theta. And then this length right here on our secant line is secant theta. Now here we've got an acute angle here, theta. And so you can verify using right triangle trigonometry. For instance, if I look at for this right triangle, it turns out that our tangent line and our radius right here also form a right angle. All right, so that's a right. We got this blue right triangle here with an acute angle theta. And if, for instance, if you take the opposite side over the adjacent, well, the opposite side here is tangent, and the adjacent side is 1. Opposite over adjacent is tangent theta. So that jives. This big triangle here, that makes sense for our unit circle. Now, there are a few other lengths in this picture. Okay, if instead of looking at the length of the line, the perpendicular that we drop from our point of tangency down to the original secant line, we look at the line that we perpendicular from our point of tangency over to the perpendicular of the secant line. I'm going to draw this in red. This length right here is cosine of theta. Right, so there's a mirror, there's a mirror here. All right, this one is sine. This perpendicular is sine of theta. That perpendicular is cosine of theta. If we on our tangent line, if we go down to the original secant line, that length is tangent. the mirror image of this, if we go look at this length right here, this is cotangent of theta. And then finally, I guess I could have traced these out in the colors instead of using those brackets. If I look at the length of this line segment here, maybe go with a little bit of a fatter red. The length of that line right there, you guessed it, instead of being secant, it's cosecant of theta. Right, so we've got the all of the co-lengths are on one side. All of the non-co-lengths, we've got sine, tangent, and secant, are on the other. Okay, now here's the part that's maybe gonna blow your mind. If I look at, there's another angle in this picture. This angle here, I'm gonna call it phi. Phi is the complement. I'm just gonna call it co. Short for complement. Come on now, give me the eraser I want. Or give me this, I want this. I don't accidentally erase thing. Phi is the complement of theta. Now that's not notation that we're using in class here, but phi is the complement of theta. And if we were focused on the angle phi instead of theta, this cosecant of theta is actually secant of phi. And cotangent of theta is tangent of phi. And cosine of theta is sine of phi. All right, if you rotate and flip this picture the right way, then we got our secant, tangent, and sine, not for phi, sorry, not for theta, but for phi. So, all right, cosecant of the angle theta is the same as secant of phi. And we just said that phi is the complement. Cosecant of theta, cosecant of theta is secant of the complement. Come on now, we're making a big secant of the complement of phi. So here's where that co comes. Here's where that co comes. The cofunction of the angle is the function of the complement angle. There's where these co's come in. We see the co's all up in the picture here. All of the co's of theta are related to functions of the complement of theta. All right, so I guess this picture here helps us understand kind of geometrically, or we get some etymology. We got this tangent line where the tangent corresponds to touch, and the secant line where secant corresponds to cut, and the tangent of theta is a length along the tangent line, and the secant of theta is a length along the secant line. So we get a little bit of insight into where those words come from. But we also see a picture where we've got all of the non-co's lengths on one side and all of the co-lengths on the other side. So we can see how the co's go together and the non-co's go together. So if you're worried, for instance, like, hey, this cosecant, the fact that it's the reciprocal of sine, a lot of people think that, well, why don't we just call that one the secant, since it's the reciprocal of sine and it goes with sine. That would be nice. It might make more sense language-wise, but as far as the geometry goes, the cosecant's over here with the cosine, and the secant is on the same side as sine. Historically, like in our class, we talk about the big three trig functions, sine, cosine, and tangent. Historically, the big three trig functions would be sine, secant, and tangent. But it turns out that secant is less useful for modern mathematics than cosine is. So that's why we kind of do things the way that we do them. All right, so I think that's all I have to say in this video. I hope you got a little bit of something out of it. If you did, send me a message, let me know. All right, if you didn't, then I guess you don't have to tell me that you hated my video. But if you got something out of it, let me know. That way I'll know if it's, I should show this video to other students in the future. If you do have any questions about this video, please let me know. Otherwise, we'll see you in class. Thanks for watching.